Hello, it's Keith here, and this is lesson 3 of the multi-platform series of my Z80 tutorials. Now, we've looked in the past in the platform-specific series at how to read characters from the keyboard and how to print them to the screen using the firmware. And in the multi-platform series in the past, we've had a look at how to process characters and how to read in whole strings from the user. We're going to extend that today, and we're going to take those previously entered strings and we're going to actually process them and pass them as commands so that in the future we'll be able to perform actions based on the commands the user has entered. So let's make a start today and have a look at the code we're going to create. Now, I should point out we're going to do everything on the Amstrad CPC today, but that's not to say that this code doesn't work on all of the systems that we've been covering in the past. So this will work on everything from the MSX to the TI-83 just fine. And that's because the only code that we're using to actually access the hardware is the code that we wrote in the platform-specific series, which works in a common way on all of the systems. So today we're going to process some simple commands, and let's have a look at them down at the bottom of the source code. You may actually notice today the source code is a little bit bigger. I had a few comments from people that the assembly was a little bit hard to read, so I've changed the font a little bit, made it a little bit larger. So please let me know what you think. Do you prefer it at this size, or would you prefer it to be smaller again? Okay, thank you. So you'll see we've got some simple commands here, some directions, some actions, and a few objects. And if you can't guess at this point, we're going to actually use these in future lessons to make a bit of a spoof of a text adventure game. Not a serious thing, just a simple game with a few rooms, a few items, and some actions we can perform on those items. And this will just be, firstly, something we can have a bit of fun and see working, but actually something you could use as a template and extend it if you wanted to make it into a more full-blown text adventure. But just for our purposes, it's going to be very simple and just a little bit of fun. But you can see we've got some commands here. So the way the program works is it can read up to 2 commands. So we can type in commands like take C64. If we hit enter, and you'll see it returns 2 numbers. And the commands start from 0. So you can see command number 3 is take, and that's why the first of those returned values is 03. And then C64 is number 8, and you can see there the second command was detected as 8. And we don't have to enter 2 commands, we can just enter 1. So we can just type in look, and you can see you get 02 because command 2 is look, and then you get FF because the second command, well, it wasn't 1, it wasn't recognized. Now also there is a sort of safety net that if the user types in multiple spaces, those extra spaces will be ignored. So if I type in take space 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 C64, you can see both of those commands were perfectly detected correctly, even though I put a lot of spaces in between. So we're detecting those multiple spaces, but we're combining them sort of into one for the purpose of detecting our 2 commands. Of course, if you wanted, you could extend this to 3 commands or more, but I thought for the purposes we require, processing 2 commands or processing 10 is functionally very, very simple, and 2 commands was enough to give us the functionality that we will require for our basic text adventure that we're going to write in the future. So we'll start by looking at the sort of top level code that is actually processing the actions of the software, and then we'll look at the new functions we've written for actually how to treat those strings and to process them and work out what they're actually doing. So first of all, we're just showing this input prompt message to the screen, and this is my spoof DOS prompt kind of message, which is just chibi : and then the arrow, or C : arrow, because on the TI-83 the screen was too small. Now, why are you doing this? Why am I doing this, you may wonder? Well, it's actually just a bit of a sort of test to make sure the wait string command is working correctly. You see the wait string command, we can type in hello, but then we can also delete it again. But no matter how many times I press the delete, it shouldn't go and overwrite any of that prompt. And you can see that does work correctly. So that was just a little bit of a test to make sure the wait string was working and not overwriting the prompt. Now, once we've read in a string, we're doing a little bit of a trick here. We're expecting to read in 2 strings, but just in case the user has actually only entered 1, we're kind of putting a dummy string onto the end, a character 0 followed by a character 255. Now, if you remember, character 255 is what our wait string command uses as its end of string function. And we'll come into that in a little bit of a moment. We'll see why we're adding an extra character 255 to the string. So the first thing we need to do, our strings are all uppercase because we're using these for functional commands, not for names or anything where case is relevant. So we just want to get everything nice and simple for our comparisons. So we convert everything to uppercase. Next, we look for our spaces in our string and we convert them to character 255s. The reason we do this is our software, our string functions are all designed to work in individual character 255 ended strings, and we want to process the user's entered data as a pair of strings so that we can treat them as two individual commands. So by converting the spaces to character 255s, we've split the one string into two. Now, of course, if the user has entered multiple spaces in the middle, that will cause us a little bit of a problem because we will have to skip over those extra character 255s, but that's still relatively easy, and this I thought was a nice way of making the two strings separate but using our existing code. Then we just print a new line to move on to a blank line. We've got our word list, which is an array of pointers down here. This is our word list here, and you can see we've got these addresses, and the addresses are actually pointing to the strings themselves. And the reason we're doing this is it's actually easier in the long run for us to have a set of addresses that point to the strings rather than just having the strings themselves. Now, in theory, we could process the strings one by one and just read through each character until we got to a 255 and then just carry on with the next one as we're comparing. But while that may work for a basic compare command, it's not very flexible in the future. We may want to print string number 8 to the screen. Now, because we've got this array here and each entry in the array is 2 bytes, we can just move down 16 bytes and we will know we will get string 8 from the array. And so by having this array of pointers that actually point to the strings rather than the strings themselves, we gain some quite important flexibility. Now, that may not seem clear to you at the moment, and this actually may be a little bit confusing for you if you're not particularly familiar with these kind of memory pointers, but don't worry about it, because we're going to come to this later when we extend this program to be a much larger, much more substantial text adventure, and we're going to do a lot more of this kind of thing then. So don't worry about it if you don't understand it, but just trust me, this is a good way of having an array of strings and being able to process them efficiently in assembly language. So we're going to read in our word list, the pointer to our word list array. We're going to read in the pointer to the test string at DE, and then we've got this command called scanList, and we'll have a look at that in just a moment. Scanlist will return the first of the words. We show that to the screen with the show hex command. That will only show the first word, and then we go on to process the second word. So what we're going to do is we're actually going to use our CPIR command. Now, quite curiously, this is a command I never actually used when I was developing Chibi-Akumas. CPIR is a compare, increment, and repeat command. So what it does is it starts from HL. It then processes as many as BC bytes, and it looks for whatever byte was in A. Now, we want to compare up to 255 bytes, and we actually want to look for character 255. So I've done a little bit of a trick here. We've loaded BC with 255, which will of course mean that A is 0 and that B is 0 and C is 255. Now we want A to also be 255, so we just load A with C. This is 1 byte more efficient than if I'd done things like this, but it has exactly the same function. So just a little bit of a saving there. And then our CPIR command will process through the string until either BC is 0 or it finds the result. So by the time we get here, we're now ready to actually process our second command. Now, the first thing we have to do is we're just decreasing HL here because the loop will increase it. And then what we're doing here is we're just going to make sure there are no middle spaces, there are no remaining spaces here, extra spaces, sorry. So what we do is we read in a character from HL, and then we want to compare it to 255. But there is a neat little trick for comparing something to 255, and that is we increase it by 1 using ink. If it is 255, it will then become 0, and we can then jump, if 0, to skip spaces. So we're going to repeat round here so long as A is 255, and we had to decrease HL here just in case it never was. So this could be again written as, this ink A here could be written as CP255, but that's a 2 byte command, and ink A is a 1 byte command, so we've saved a single byte there. Next, we need to swap HL and DE because we need the next memory location to be in DE like it was up here. We then load our word list in again and run the scan list command again. Finally, we show the second hex character, start a new line, and we jump all the way back to the top and read in another line from the user until the user gets bored. So, how are we doing our scan list? Well, we'll have a look at that in a moment actually. First of all, let's have a look at our new string functions. We're using the same string function before the toUpper command. This was in a previous lesson, so we won't cover that today. But we do have some new commands here. Now the first one is very simple. We've got a command called replace char, and all it does is it reads in a string from HL. It waits until it finds a character 255, and when it does, it returns. Now you may think, well, why aren't we doing INKE there as well in the same way as before? Because that would have saved us 1 byte. Well, there's a problem with that. It would save us 1 byte, but it would also change A. So it's only appropriate if the only reason we're reading in A is to do that comparison. In this case, we've got another comparison following it. So if we've done INKE, it will no longer be valid for us to do the compare to D. And D is the character we're looking to replace. So in this case, we can't use that saving. So our CP255 is more appropriate. So we compare to D. If it's not matching, if A isn't matching D, then the character isn't something we want to replace. So we just skip over this next command and carry on throughout our loop. If it is a character we want to replace, we simply put the replacement from E into HL, and that will do it for us. And that's everything the replace command does. It's very, very simple. Now, when it comes to processing our list of strings that are in that pointer array, we've got two parts. Firstly, we've got a command that compares two single strings, and then we have a loop that uses that command over and over again on each of the entries in the array. And that, while it's probably not as efficient, we could merge those two commands together. Having a compare string command that does the compare for us, and then a loop that processes the array, makes things a lot nicer and neater. And if we were doing a large program, we may be able to get an overall saving in space, even if we don't get a speed saving. And of course, because we're writing a text adventure, speed isn't going to be an issue really. So compare string is very easy. It takes in one string in it takes a pointer to one string in HL, another string in pointer in DE, and then all it does is it loads the first byte in from DE, compares it to the byte in HL. If it's different, then the string's already different. Now, when we return from this, we actually use the carry flag because that's easier for doing our comparisons, and we can quickly set the carry flag using the SCF command. So if the strings don't match, we just set the carry flag. This command, of course, can't detect if something is greater than or less than, and as two separate results. It can only say these strings are the same, these strings aren't the same, and that's all we need today. But there may be sort of sorting cases where you need to know less than, greater to, or equals, three different options, but this doesn't provide that. So that may be something you may want to add if you need more advanced functionality. But this is perfect for today. So if those two characters were the same, then we've got another comparison we need to do. Now what we want to do next is check if either of the strings has reached the end. So what we do is we've already got the DE string in A, so we OR it with the one in HL and compare to 255. Now this basically says, have either of those strings reached the end? And if they have, we jump to this end command. Now at this point we know one of the strings has reached 255, but we don't know if both have. And so what we do next is we actually do an AND command and see if both are actually equal to 255. If they are, then we can return, and if they haven't, then we will return as well, but we need to set the carry flag first because the strings are obviously different length, and so by definition they don't match. Now, just one thing to notice here, we never actually clear the carry flag here. There isn't actually an individual command to clear the carry flag. CCF is actually complement carry flag. It's not clear. So one option is SCF and then CCF, which will clear the carry flag. But actually our AND command here as a byproduct is clearing the carry flag, so we don't need to do anything in this case to clear the carry flag. And most AND or OR commands will clear the carry flag. So that is actually quicker than doing SCF, CCF, and OR will have the same effect in 1 byte compared to those 2 byte commands. So this function here will do our job of comparing the DE and HL strings, and the carry flag will be set if they don't match or cleared if they do. So that's what we need to do to compare one string, but of course we need to compare an entire array of strings. So let's have a look at how we do that. So as I've said, we've got our strings here, we've got our pointers to our strings here, and you'll notice that each of these is 2 bytes because they're an address of the string itself, and then the last one is 2 bytes, both of which are FF. So that is our kind of marker. We're using the character 255, a pair of 255s in this case, to mark the end of the array. So let's have a look at how we scan that list. So we're using self-modifying code first because we need to we need more registers than we have available. So we're just backing up this and copying it down to here for our compare string command. So we do that. Then we load our count as 0. And this is the word that we're currently looking at so that we know what to return if we actually find a match. Then we load in E and D from HL, and this will of course read in one of these pointers. Next we need to check if both are 255 to see if we've reached this end command here. So all we do is, like we did just a moment ago, we load E into A and in D. We do our inc of A because at this point if either one was 255 but the other wasn't, then the result will not be 255. It will only be 255 at this point if both are 255 here because of that AND command. And if the result in A is 255 at this point, increasing it will again reach 0. So at that point we've got to the end of our list, and this function will return only the first command. Because we're doing an exact comparison, we're assuming there won't be two commands in the list that are identical. If there were, then it would return the first one. But that's not a problem in this case because it's a list of commands that we've predefined. So at this point we would return and return 255 because we've failed to find the result. But if we get to here, then we're going to try another. We found another string we can try. So we load back in the string we want to compare to that we've updated with our self-modifying code here. And then we run our compare string function that we just looked at over here. Now, as I said before, this will clear the carry flag if it was found, or set it if it was not. If it clears the carry flag, then we found the result we wanted. So we jump to found, load B into A, B being our comparing string and A being the result. We found the result, so we just give it back to the calling function. If we haven't found it, we increase B because we're going to move on to the next command, and we jump all the way back up to here. And of course, this function would have been called when we got to the end of the list if we'd not found a result. So we just set B to 255, and then we will set A to B and return here. So there we go. It's quite a simple program this week. I'm going to extend it quite a long way, and I've actually got some more exciting things we're going to do with this later. We're not really going to take it too far with regards to text processing. I'm planning next time you see this code for it to have a simple description of the room, some objects in the room, an inventory system, so you'll be able to take the objects, perform actions in the room, but we're not really going to take it any further than that, and there's a very good reason for that. I've got far more interesting things that I want to do beyond text processing, because I think at this point you can probably see how we're processing the strings, and if you know a bit about ASCII and you've sort of got some basic ideas of how you would process strings in BASIC, you can probably work those kind of things out yourself. So what we're going to do is we're going to do far more interesting things, and we're going to start adding music and graphics to our text adventure. So we'll have little pictures of the rooms, albeit only 2 of them because that's all I'm planning to do, but we'll have some music and some text and some graphics with the text so that we can start to feel like we're programming a full game. And as I say, we're not going to program a full game, but I want you to show you enough that you could then take this and make it into something of your own later. So anyway, that's what we're doing today. That's what we'll be seeing in the future. So I hope you'll subscribe to my channel and watch those later lessons, because I think I can make something that's really going to be quite enjoyable for you to see, and hopefully will inspire you into making it into something of your own that's way beyond anything that I'm going to show you here. As always, the source code for this lesson is available on my website, so just go ahead and download it. It's called String Match. All of the examples are available, so yep, just go ahead and try it. And as I've said before, this will work on any of the systems, whether you're a CPC user, MSX user, a Spectrum, Enterprise, Sam Coupe, or a TI-83 user. This will work on everything exactly the same, and you will only need to write your game once, and it will work on all of those systems because of those common functions. Thanks for watching today. I hope to see you next week.